students who've worked with Jeremy have done in the makerspace, but one of the other aspects of his work here at Sonoma State is community engagement and identifying community partners with whom to work. And our final speaker has undertaken his project with one of those community partners, or in that sort of modality. I believe you're also a runner-up finalist in the Science Symposium?
Yes.
So,
Yeah.
So, setting that expectation sufficiently high, let's welcome our last speaker of these days, Sean.
Thank you, Dr. Target. My name is Hawkins, and I did my research on reduction in thin film curvature post-deposition. Now, I have been a student at Sonoma State for 2 years now. I transferred from Santa Rosa Junior College. Through all of my studies, even at Santa Rosa Junior College, I've been working actually in the thin film industry. I have been working with Alexa specifically for the past 2 years, and when I approached them with the idea of doing research for them, at the same time of getting credit for my schooling, they obviously accepted because free student doing some stuff. So let's go ahead and get started. So in order to understand the breadth of my research, you need to really understand what exactly thin film is. So as you see here, I have a diagram which contains a substrate here, which is typically made of glass, different variations in glass, depending on the properties that you need to work with light. On top of this glass is alternating thin layers, ranging from 1 nanometer thick, which we already heard about how thick nanometers or how small a nanometer is, to a couple hundred nanometers, especially at our company, that's not the typical range. Other companies can go thinner or thicker, obviously. It all depends on the application and what they're actually producing. So filters are coated on a large substrate, which we call a wafer. Typically the ones that we coat are about 6 inches in diameter and are fabricated down into various parts for the specific device that they're going to be used in. These fields can include astronomy, life sciences, material science. As you've seen in not the LiDAR system, but in the, excuse me. Oh, sorry. So yes, so they're using the LiDAR system, and they're also used in interferometry, which is really interesting for this project. So understanding thin film filters, what we basically do with thin film filters is we manipulate light. Manipulating light in certain ways, it depends on the application for the light. So as many of you know, light is broken up into a spectrum. If any of you have seen Pink Floyd's famous album, you've seen the prism rainbow coming out of it. So looking at the spectrum here, there are 2 main categories, and then the visible spectrum, which is what we typically see. Down here is the ultraviolet, up here is the infrared, as we've seen in the other presentations as well. I have a couple examples of typical filters, such as the bandpass filter, which allows a wavelength of light to travel through it and reflects or blocks out the lower side and the higher side. The other type of filter that's typical in this industry is long pass filters, which allows the higher wavelength light to go through the filter and block out the lower side. The opposite of that is a short pass filter, which allows the low wavelength light to transmit and blocks out the higher wavelength light. Now, there's also another filter called the notch filter, which is essentially almost the inverse of a bandpass filter, where it blocks out the center wavelength of light and transmits the higher and lower side. I included here also a dichroic long pass filter, which we'll get a little bit more into because this is a primary aspect for interferometry. So now that you know what thin film filters are and what they do, why is stress bad? Why is curvature bad? Why am I doing this research? The problem with curvature is it does things to light that is not ideal for your system and can cause issues. So looking at this picture here, this is a very simple, oversimplified picture, but essentially you have light hitting your filter coming out straight. That's the ideal perfect filter, never happens. Now, light hitting a curved surface comes in and then comes out normal to the surface, so it kind of goes in various directions. This can cause a couple different types of aberrations or distortions, such as a spherical aberration, which is where you have light at the center, and then you have a ring of dark, a ring of light, a ring of dark, a ring of light. Obviously, like this screen moving right now.
It's a dynamic effect, yeah.
If you You also have issues such as an astigmatism, coma, wavefront distortion, or chromatic aberrations. Astigmatism, I'm sure someone in here has probably experienced that or knows about it, where you have light that focuses in different planes. So for example, astigmatism is where light will focus in on the horizontal plane but be blurry in the vertical plane, or vice versa. There's also chromatic aberrations, which is especially an issue in the thin film industry, especially if you're trying to focus various wavelengths of light coming through a filter. In that example, what happens is light comes through in different wavelengths, and they all come to focus at different points. This causes issues in your system, which you do not want to have to experience, because then you have to tweak your filters and tilt them and do all kinds of different weird things. Example of a coma is, as you see here, it comes into focus at different planes. It's similar to, it's basically based off of a spherical aberration, but it comes into focus more at this point here and kind of rings out. And again, I just discussed the astigmatism. Now, interferometry. This is the system I was discussing earlier, and this is the focus of my research. So up here I have a simplified image of how an interferometer works. So you have a light source. It goes through a small field stop, which is just basically narrowing down the path of light, and it comes into a system and goes through a beam splitter, similar to LIGO. Now, what this does is, similar to LIGO, it sends light this way and sends light this way through the beam splitter, splitting the beam. Now you put your substrate down here, and as you can see, there's little pitches here, and as you kind of move it around and take a measurement, you will have a different distance that this light travels up to the detector, and then this light that's reflected up here from the beam splitter. This gives you an interference image. Now, as you see here, I have an image of my substrate. This is actually the outer edge right here of the substrate. This right here is what I could get into focus with the curvature. That's how bad the curvature was on the system, or for the substrate. As you see right here, there's this small yellow circle here. What that is called, and it's an aperture. I'm aperturing down the light to essentially this is a 1-inch aperture, so I'm looking at only an inch in diameter of the substrate. So with this, you can see that I have a really good image here, but out here, I have a lot of reflection, and I could probably align out here if I had to, which I did for some of the other measurements, as I'll show in the next slide. With my data collection process, what I did in my contribution to this was, typically right now, we just measure a single point in the center on the substrate, and we take that as our measurement because theoretically that's where we believe the worst variation for the thickness would be. Now, what I did was I measured out every inch for 3 inches with that same 1-inch aperture every 90 degrees, giving me a bunch of measurements to average together, look for the maximum or the minimum, and be able to put it into a calculator in Excel, believe it or not, which took quite a bit of time using a lot of the formulas I had to use. And I was able to get profiles from the interferometer like this. Now, for the rest of the talk, I'll be talking in PV, which essentially means peak to valley. So if you look at this image here, the highest point is obviously the red. This is the peak. The valley is down here at the blue. So this is my 1-inch aperture, but it's showing a 3D profile of what you're seeing. So if I go back one slide here, that's what this image looks like in 3D. So as you can see here, it's kind of small, but everything's measured on an interferometer and fractions of a wave. And for this one, you can see that this is a plus 2.43, and down here is negative 2.77, so you have a variation total of about 5, give or take. Now, here's my results. So I had 2 substrates originally to work with, this one and this one. So substrate 1, substrate 2. I took the averages of all the values, and I derived a process in my Excel calculator, if you'd like to call it that. And then I did the same thing for this maximum method. Both of these were very similar in shape, where it was convex curvature. And so for this method, I did the process, run it through, and it actually flipped in orientation. Now, this doesn't look necessarily flat either, but that just shows you the resolution on the interferometer. Because if I go to the actual fraction of a wave, this is a variation of about 5 between the two of them. This is at 0.35 and 0.43. So if you actually plot these on Excel, you can see that this goes from about an average value of -6 or so, all the way down to almost near 0. So this substrate was actually very flat, past specifications for the customer, and is in inventory to be shipped to the customer as a product. The second one here, this one shifted a little bit, but not much. So this one, for the scale here, is plus 0.69 and minus 0.79, so it was pretty close to being within spec. It was just a little bit out. So I tried the maximum point for the variation for the PV, and I used it to, I used my other process using the maximum method for this one. And this only changed to 0.52 and minus 0.25. So it still ended up being within specs and actually is, again, in inventory for the customer. So yeah, great. Two substrates that are both passing. And I feel like, okay, I succeeded. But I wanted to test this one more time using another substrate because we had one more substrate and I had enough time to be able to squeeze it in. The issue I ran into though was that this substrate was different. It was curved in the opposite manner than this one was to start with. So I wanted to test this process on this to see what would happen, just as an experimental confirmation. So with this one, you can see that the highest point here is at 0.47, the lowest point down here is at negative 0.22. So it's actually pretty close to flat, but the thing is that the variation across the substrate is all over the place, so it wasn't very good, so I used the averaging method to give me an average of all the variation. After applying my process, this reduced down to 0.37 to 0.34. This allowed me to get close to zero for the measurement I was actually aiming for. Unfortunately, it didn't work enough to bring this wafer into specifications for the customer, and I believe that to be a product of this starting curvature compared to this starting curvature. So overall, I put these two side by side so you have a better comparison. You can see that the stress on this one and this one at the end both look pretty similar. Obviously this one being worse than this one. So what I would like to do with my research is continue testing more substrates that I can find that are failing due to this sort of curvature and try my process again on those to see if I can duplicate the result. But unfortunately, during the time when I was doing this research, I only had 3 substrates to work with, and one of the 3 was different than the other 2. So I would like to continue doing that, but then I would also like to be able to look at methods into bringing this type of curvature into spec for customers in the future. Overall, I think the experience was great. I got to work by myself in a lab with the interferometer that I've worked with as a technician and not really known too much about or how it worked. I was able to, like I said, 2 out of 3 of the substrates passed, which is awesome. And I was actually offered a job out of school for this company, so I'll be working there and hopefully continuing on this sort of research to bring some of these things back to the spec. And the reason this is an important thing is that if it's not in spec, we will just scrap the wafer of the substrate and it's just over with. We're done. We'll just coat it again and hopefully it comes out better than the last one. With this, if I can do this after the substrate's already been coated, then I've already done I've already done something that would help save us money in a sense. And the money can range in the value of the part too. So some parts on average can run from $1,000 a part down to $20 a part. It depends on the customer, it depends on the difficulty of the spec. With that, I'd like to thank Dr. Qualls for his help on my slides, my symposium poster. I would also obviously like to thank my employer, Alexa. Without them, I wouldn't have had any research to do with this. And also, they paid me to do it. So that was awesome. And also just the fact that I was able to use their materials, their machines, and learn on my own. The last person I'd definitely like to thank, unfortunately wasn't able to make it, is Kevin Nolan, who was the head of engineering at Alexa. And I worked hand in hand with him, so whenever I had a question, he would steer me in the right way or give me an idea of what to go with. That's it. Thank you.